Today we're talking about moving mesh. Hydrodynamics. So the idea is pretty straightforward, and we're going to hear lots of great science done with moving mesh codes later in the session. But I'm going to start by just introducing some basic concepts that are needed to do this. And to some degree, you already know almost everything you need to know just from finite volume methods. But the only difference is, we keep on drawing like a finite volume grid in solve Euler equations. And you can do fancy things like you can increase the resolution in certain regions adaptively, like BMR. But as you saw from Daniel's lecture, it's also nice sometimes to have a code that's kind of Lagrangian. So anyway. And so these moving meshes can serve as kind of something that has some of the advantages both of a Godunov code and a moving mesh. So it's a mesh that moves with the flow. Yeah.
Sorry, could you introduce yourself?
Oh, I'm sorry. Oh, I thought it's hard to read from there. Right? I'm Andrew MacFadyen, and I'm from NYU, so just down the street. Okay. Right. Here's my email.
Andrew, just on the recording, you want to stay to the right of the word mesh.
Oh, so here? Wait, what?
To the right of the word mesh.
The right of the word mesh, okay. Okay, so the basic idea, though, is that in order to try to move, for the mesh to move with the flow, is the faces themselves are dynamic, and they can move. What we want to understand is how to solve for the flux or the motion of mass, momentum, and energy across a face which is moving. And that's basically the whole thing I'm going to tell you today. So this is the moving mesh, right? And so a little bit of history. This was very popular in 2011 when a repo came out, a really important code for cosmology. But as usual, mathematicians have done this a long time ago. These are people at NYU, Borgers and Peskin, did this in the 80s. So it's usually about 25 years to get from, or often takes that long to percolate into physics. But they were interestingly working on, they're physiologists, they were working on blood flow and around heart valves, which move in response to the blood pressure. So it's nice to have a mesh like this because of the boundary conditions that can be flexible and move. Okay, so so the basic idea, though, is that cell faces can move at any velocity. They can move in principle faster than the speed of light. It doesn't matter. It's just not a physical thing, the mesh. And, oh, and sorry. And then Borgers and Peskin was the first one. And then famously is the repo, right? Springle. And then today we'll hear about Manga by Phil Tang, who's here. And TESS is a relativistic MHD code written by my former student Paul Duffel. And Rich is written by some Israelis. And there's probably more by now, I just don't know. Okay, so the basic idea is that cell faces can move at any velocity by peeking into the Riemann solution. Now, to some degree, the Riemann solver in a code can often be thought of as kind of a black box. You give it two states on either side of an interface, the primitive variables, and it spits back a flux of mass, energy, and momentum. And you don't really need to look sometimes, but it turns out to do this, you do. And so we want to look inside the Riemann solvers. I'm going to talk a little bit about Riemann solvers. You've heard about them already at this school and probably previously, but I'll focus on what is important for getting meshes to move. Okay, so as we've seen many times, the basic idea for finite volume, and we're just going to stick to 1D for now, because you'll hear about multi-D later. So the basic idea is in 1D, you just split things up into cells. And then we have volume average quantities in each cell. And then the whole name of the game is this interface where we want to get the fluxes, which is a solution, which come from the solution to this Riemann problem. The Riemann problem, of course, is just two constant states separated by a discontinuity. The important thing is this discontinuity doesn't have a length scale associated with it. There's no length scale here. And because we're time step limited, we never see the edge. So we can think of this Riemann problem as being infinite in both directions and just having a discontinuity at the zone interface. Okay, so that's, if this is zone I, we label this face I plus half and the left face I minus half. And so what we want is these fluxes at the interfaces. Okay, so, so is this clear so far? Okay. So the basic problem, Riemann problem then, you can think of as the resolution of two states, U left and U right. And you can think of these as going forever. And then this solution resolves into some nonlinear waves, which we're going to talk about. There'll be a shock, in this case, moving to the right. There'll be a contact discontinuity, which is the zone interface at the beginning, also moving to the right. And there'll be a rarefaction wave traveling to the left, communicating to the gas to the left that gas is moving away. Okay, so so this thing has, since there's no characteristic length scale in the Riemann problem, the solution found by Riemann is self-similar. And that means it's valid for all x and t. Okay, so the initial data that we give is, so this is the tuple of conserved variables, rho, mass and momentum and energy densities, as a function of x at the initial time 0. And so it's a very simple initial condition. It's the simplest, interesting one, that it's u left if x is less than 0, and u right if x is larger than 0. Okay, and so these are, this is a piecewise constant initial data. Okay, and so this is the famous example of that is something you can just set up in this room easily. It's called a shock tube. You just have a tube and you put a diaphragm at x equals 0 at the beginning, and then you pump up each side to some pressure on the left, some density on the left, and some velocity on the left. And then on the right, you have some right pressure, right density, and right velocity. And then at t equals 0, you remove that barrier, and if this pressure is higher, it'll drive this shock wave, And then this interface will move as the contact discontinuity, we call this. Then the rarefaction fan will propagate to the left. Okay, so in principle, for this setup, this would be the shock. This is the contact discontinuity. Continuity. And this is the rarefaction fan. And this is its head, and this is its tail. So this is some sort of structure. And so both of these waves are nonlinear waves. And so the solution is found iteratively, as I'll show. How far over here? Can you go all the way?
Yeah. Almost.
Oh, I see. Yeah. Okay.
You can get going.
Even further?
At the edge.
Oh, to the edge, okay. All right. Okay, and as you've seen, for this initial condition, what happens is you have your two states, which are initially like this and that, but the shock propagates here. There can be a contact discontinuity, and then there's a rarefaction fan like that. Right, and this would be for the density. In this region here, between the waves, the pressure and velocity are constant, but the density can have a jump. So as a function of time, what happens is this thing just expands similar to itself. So you could rescale the solution so that it's the same solution as a function of x over t. So the point is that u of x at t1 and u of x at t2 are similar. So the solution really depends on the ratio x over t. And then for the finite volume methods we've been using so far, or discussing so far, what we want to know ultimately is the flux at the zone interface, which is at x equals 0. So the purpose of solving the Riemann problem is to find the pressure, density, and velocity at that interface, which is, since this is self-similar, that's a constant in time. So that those interface values don't change, and so that's really useful. So once you've solved this problem, you know what the interface fluxes are. Okay, so the solution depends on x over t, and the solution is constant at x equals 0. That's what we use for finite volume codes, static mesh. But the key point is that if you look at this in terms of the waves, here's x, this shock travels at the shock speed. This wave goes at the contact. This is the shock. This is the contact discontinuity. And this has some speed, s shock. And then there's s contact discontinuity. And then there's the tail and the head, the rarefaction fan. Okay. And then the point is that this solution is self-similar, so it has the same value along x equals 0. But the key idea, it's a really simple, basic, obvious one, is that we also know the solution along any characteristic. So you could move at any velocity you want in this diagram. And if we have the full solution to the Riemann problem, then we know what the fluxes are with respect to a face that's moving in space. And the only thing, so that we'll get that flux from the solver. And the only thing we have to correct for is an advective flux. If you have a surface that's moving through some density of something, there's the density times the velocity, which we have to correct for the vector flux. Yes?
I was just curious, so by the way you've drawn that, because I've always thought about the intermediate state as being basically the state immediately behind the shock. And you've drawn it sort of in the middle of the rarefaction.
What have I done, sorry?
In the diagram above, you've drawn the jump between the cells. Sort of.
Oh yeah, it's in the rarefaction, it can be. Yeah.
That makes sense, but
Yeah.
so is it obvious why it doesn't change with time?
It's because of self-similarity. You can do the characteristic decomposition of Euler, and you'll find that it's self-similar. So it's just, at a later time, it's just going to have expanded out. But yeah, you're right. The usual way to see this.
So you're still in the middle of the rarefaction at some later time, just in a different middle of the rarefaction.
Yeah, but it has the same value.
Yeah, gotcha.
Yeah, that's the key point. Yeah.
Yeah.
Okay. And so these are these nonlinear waves. Okay. So the point is, the main point is that the solution is constant along any characteristic. And a characteristic line is something of the form x is some speed s times t. Okay, so what that means is if we have a mesh face that's moving now, we can calculate what the flux will be at that interface. And so what this looks like is, remember our update formula. So U at some zone I, that's the vector of conserved quantities, is U at I times dt over dx times these numerical flux functions that come from the Riemann solver at each interface. Okay. What we could really do, and we're going to need to do this for a static mesh, delta x is constant. It's the same everywhere, and it doesn't change in time. So what we can do is just multiply this equation by delta x. And then, so delta x times u is like the total mass in the zone, the total energy in the zone, and the total momentum in every zone. But the thing is, with a moving mesh, this delta x can change in time. So we have ui at n plus 1 times the size of the zone at, oh, and by the way, the indexing, just to make sure, I is spatial and n is the temporal index. So that equals ui n delta xi n minus delta t times these fluxes, these flux differences. So here's what we have to do. We find the flux along a ray in the Riemann problem. And then we subtract off the velocity of the face times the values of the conserved quantities at the interface. So this is the effective flux that I talked about when the face is moving through something. Yes?
Sorry, what are the subscripts on the fluxes? The I
Oh, I'm
plus-
sorry, that's I plus half and I minus half.
Gotcha, thank you.
I plus half, I minus half. Okay. And so, and then that's minus f I minus half minus w I minus half times u I minus half. Okay, so that says, like, for example, the mass in the zone at the new time is the mass in the zone at the old time minus, or the time step times the flux found from this Riemann solution minus this effective flux, and that's it. That's a way to write. You could know now how to write a code where you can specify the velocity of the faces. And you can specify any velocity you want, or you can choose some interesting velocity, like for example, the speed of the contact discontinuity. Okay.
So
Yes.
for that equation, that's a new term.
Which is, sorry, that was a mistake. Sorry about that. Is that okay? Yeah, so it's a new term, the flux. Before it was just the flux, right?
Yep.
But now it's the flux minus this term.
Oh, I
So
see.
the face is moving at speed s, and you just subtract that. Okay. So you just use the Riemann flux along your characteristic s, and then in your update formula, you just use that flux minus s times u. So effectively what you're doing is you're just subtracting this. Okay, and then we can write this let's see, let me just squeeze it in here if you don't mind. So in multi-D, it would just be this vector n+1 times the volume of the zone is the old values, and then minus delta t, and then a sum over the faces that are bound the faces of I. And then the flux between I and the neighbor zone J minus the velocity of the face between I and J dotted into N Uij dA. Sorry, it's behind there a little bit. Right. Okay, so when I was writing this, I figured you guys might be a little bit sick of Euler. It is the system that we use all the time to study because it has a lot of interesting properties. And we've seen previously, you can extend that to MHD. But I thought I'd just show you very quickly that everything that here that we've done applies also to relativistic fluids, which is what I'm mostly interested in. And so I just wanted to make clear, just quickly, that this exact same formulation works in the relativistic case. And so this is another system you can think of if you want to solve hydro. So special relativistic hydro SRHD. And so you have the same thing as with Euler, non-relativistic fluid. It's just conservation of mass and now energy momentum from the energy momentum tensor. And so you get kind of these divergences. So this expresses conservation of rest mass. And this expresses conservation of energy momentum. And then for special relativistic ideal fluid, the stress energy tensor or the energy momentum tensor is just the mass density times the specific enthalpy, h, little h, times the 4 velocity minus the pressure times the metric. Okay, and whatever, this doesn't really matter. This is going to turn out to be very simple. So H is the enthalpy, specific enthalpy. It's 1 plus epsilon, which is that's the internal energy, plus P over rho. Okay, and then what that means is that we can define, if we have a fluid moving through this room at some velocity, say this is a fluid element, if it's moving, it's going to be Lorentz contracted in our frame, right? So in the lab frame, the density will go up by a factor gamma because its volume is contracted by a factor gamma. Is that clear? That's all. That's super simple. So that's just, so what we do when we do a computer program in relativity is we choose a lab frame or a computational frame, and then we define our quantities in that frame. And so it's actually pretty straightforward. And we call this a D. So D is the lab frame density, and it's just rho, which is the co-moving density, times the Lorentz factor. So the Lorentz factor is just 1 over root 1 minus V over C squared, but we're using units in which C is 1. Okay, so that's the mass density. The momentum comes from here, and it's just rho h gamma squared times V, component of V. Similarly, the energy density comes from the 0,0th component of that, and it's just rho h gamma squared minus P in this sort. But then that's the total energy density in this lab frame. But then we subtract the rest mass energy density, D. So we're just dealing with kinetic and internal energy. Okay. But the point is that our system is still in this form. It's still a conservation law. It's still what we're used to. But the only difference now is that U is now this. So D, S, and tau. And then the fluxes are straightforward. The fluxes are always a density times a velocity. So now the flux of mass is just D times V. So the flux and then the flux, and that's just an advective flux. That's the density D moving at velocity V, that's a flux. Now there's also an advective flux of momentum, which is just the momentum density times the velocity, that's a flux of momentum. But in the case of momentum, there's also a pressure term, because pressure gradients can accelerate a fluid and change the momentum. And then the flux of energy is just the momentum density, just S minus dV. And that's it. That's it. So everything you've done, you can make relativistic. It's totally straightforward. So you have a vector or a vector tuple of conserved quantities, and then you know their fluxes. You plug them into this type of formula like you've done before, and you've got a relativistic code. There's one minor thing, which is you can see here, as we've seen before, that the fluxes depend on the primitive variables like the pressure and the co-moving density rho. So to get the primitive variables for the conserved variables, since they're coupled through these equations, you have to do a nonlinear, you have to do Newton-Raphson, which is a little bit annoying. So relativistic codes are a bit slower because of that. But other than that, that's it. So any questions about this? Okay, so I just want to state that recovery of primitive variables, rho BP again, is iterative. so somewhat more expensive. Okay, so in this afternoon, some of you're going to be writing a piece of code using Euler, but if you wanted to, you could try relativistic instead. And I've done this a lot in classes at NYU, and it works really well, so it can be really fun. I highly recommend this. All right. Oh, and it can be extended to general relativity also if you have the metric, or if you're computing the metric, that's fine. Okay. All right. So the main point is that we need to open up the Riemann solver a little bit and look at it to find how to get the solution along characteristic curves. So, so the first step is the exact solution. I believe that's been, it's in some, I saw this in some of the Python notebooks that you have, I think, from some of the earlier lectures, but I'm just going to sketch it out anyway. So an exact Riemann solver, remember, is the full solution of the Riemann problem at all points in space-time, forever and everywhere. So it's a very useful thing to have. So this Riemann problem is a Kaushipa, it's an initial value problem. IVP. And it has the same form. And then just because this is standard, we can do it for Euler. Mass, momentum, and energy densities, fluxes, rho v squared plus p, and then effective flux of energy plus the pressure times the velocity gives the work done by the pressure forces. Okay, so the Riemann problem is just the initial condition. It just says that initially at time equals 0 as a function of x, equal u0 of x. It's the simplest thing, like we did before. It's just u left if x is less than 0, and u right if x is greater than 0. And then to solve the Riemann solution means to find u of x and t for t greater than 0 and x everywhere. Okay, so that's the Riemann problem for the Euler equations. And as previously, just nomenclature, we also use a vector of primitive variables we can call W, which is just the density, the velocity, and the pressure. Those are the primitives, and we need those to compute the fluxes. Okay. Right. So one thing that's left is getting the primitives from the conserved, and that's trivial. Rho is just rho. So if you go to the conservative variables, the primitives, rho is just the same. Then we need V. Well, that's just the momentum density divided by the density that goes to the velocity. And then P is just rho E times gamma minus 1. And little e is just the total energy density minus the kinetic energy density. That's the internal energy density. Okay, so that's the Riemann problem for Euler. Okay, and so we often draw the same Riemann problem in general. There's four possibilities. So one is what we've seen before, which is you have the contact discontinuity moving to the right, shock moving to the right, and rarefaction fan moving to the left. And then let's see. So this is 0, this is x. And then it's also possible to have the opposite direction. You have the shock going to the left. Contact discontinuity and then rarefaction fan. And then, so other ones, what are other possibilities? So remember, you have a tube, there's a diaphragm here, and you can set pressure, density, and velocity on either side of the interface. So far we had pressure higher on one side to drive the shock and rarefaction. Another possibility is the gas is diverging. So you just have gas that's expanding away from the 0, from the interface. And then all you have is 2 rarefactions. You don't have any shock. So in that case, you can get 2 rarefaction fans. And then a contact discontinuity. Right? And then the fourth possibility is 2 shocks. So if you send the gas converging like that, then it'll pile up and the shocks will propagate outwards in different directions. So what that'll look like is just shock, shock, and then contact discontinuity somewhere. Okay? So the general solution to the Riemann problem is one of these 4 things. But when we're trying to solve the Riemann problem, we don't ab initio know what the solution is going to be. So we have to be a little bit clever in doing that. The general Riemann solution is going to have 3 waves like this, 1, 2, 3. And that counts as 1 wave, 1, 2, 3. And so there's 4 states that we have. So the Riemann solution consists of 3 waves in 1D like this. And they're associated with the eigenvalues. Lambda 1, which is B minus A, lambda 2, which is just the contact, which goes up as VV, and lambda 3, which is V plus A. So those are the 3 eigenvalues of the Euler equations. And A is just the sound speed, the local sound speed. So it's just root gamma P over rho. Okay. Okay. So the 3 waves separate us into 4 different areas. And so it can look like, draw what this looks like. Here's our initial interface. And so we have this, and now we don't know when yet. For the general problem, whether this nonlinear wave is a shock or a rarefaction. So I'm just going to draw it as a double line. This could be either a shock or a rarefaction. This is the contact discontinuity. So this one goes with this speed, v plus a. This contact has speed b. And this other nonlinear wave going to the left, which could either be a shock or a rarefaction, has speed v minus a. And so let's just write this in terms of primitives. We have a left state and a right state. And now we have a new thing, which is a star state, which we call WL. We have another state, W star R. Okay, so these are states that form in the solution to the Riemann problem, right? And so we're going to need those values, P, rho, and V, along in some star region, if the face is moving along, let's say, at this speed. Then we would need W star R. Okay, so this represents nonlinear wave, unknown type. So it's either a shock or rarefaction. And the middle wave is always the contact discontinuity. So based on the eigenstructure of the Euler equations, we know that the pressure and velocity in the star region are constants and they're always findable. So this is called P star and V star. That's the pressure in this region, which is continuous across the contact discontinuity. So it's just one value in here. And then the same with the velocity. It's just a constant in this state, P star and V star. So these values are constant between the right and left waves, between these waves. Okay, and this is called the star region. Okay, and so in these, so pressure and velocity are continuous across the contact, but the density can jump. So at a contact, you can have a jump in the density. So on the star states on the left, it's rho star left, but then just E star and P star. And then similarly, the star state on the right is just rho star right, V star, P star. So solving the Riemann problem, the first step is to find what these values are of the pressure in between the waves, or the velocity and the velocity in between the waves. Let's see. Right. Okay, so we want to know how to find star V star. So the way that this is solved is by looking at your initial conditions, you can get a velocity jump across the discontinuity. We call this delta V, and it's just the velocity on the right minus the velocity on the left. So just the difference in velocity between the two constant states initially. And so we want to write relationships between P star and these waves that allow us to calculate these jumps, and we want to be able to write them as a function of the pressure. So we're going to have some function of the pressure, and it also, of course, depends on the left and right states. It's really, for our purposes, just given these two states, we just want a function of the pressure. So that's going to be a left function, which is a function of P in the left state, plus a right function, which is a function of the right state and the pressure. And we want to find the roots that solve this equation. Essentially, we want to attach across these waves jumps in the velocity such that they agree with the velocity. Once we've found that, we've solved the Riemann problem. Yeah.
Okay, so the velocity jump you have here is across like the origin, the 0 point.
Yeah.
And so the left star state and the right star state are like, they change across the contact discontinuity?
Yes.
Or, okay.
Yeah.
So make
Exactly
sure
right. Exactly. Right. Yep. Right here's the contact. Right. Yeah.
So it's constant across that, but not constant across 0.
The pressure and velocity, the density can change across the contact. Yeah.
Thank you.
Okay, sure. Let's see. All right, so here's the procedure, how to solve the Riemann problem. Given states W left and W right, which are, once you're given them, they're constants for this procedure. So given these states, iterate over P, the pressure, until you solve it, until this equation is solved. And we found the root of that equation, and that is P star. Okay, so the cool thing about these functions is as you're adjusting P, they can switch from a rarefaction to a shock, on both sides. So it's kind of cool. You're moving around in P, trying to find the right P, and these functions can either be shocks or rarefactions. So where, for example, I'm just going to write the left one, the right one is the same, except, well, very similar. And so the left one is just a function of P and the left state. And so that function you can write by using the Rankine-Hugoniot relations, the mass, momentum, and energy conservation across a shock wave. You can write this expression for FL. It's the pressure, which is the thing you're iterating over, minus the left pressure, times this constant AL over the pressure, plus another constant VL, which I'll define in a second, to the half. And that's the one you use, you're iterating over pressure. So if you do this, if pressure is larger than PL, if that's the case, you're dealing with a shock. Because the star state has a higher pressure than so if you have a shock, the pressure increases across the shock. And then similarly, for a rarefaction, that would be, again, from gas dynamic Euler equations, you can find this expression for the rarefaction fan. So that's gamma minus 1 or 2 gamma minus 1. So that's if P is less than P. Then you have a rarefaction. Okay, where AL is 2 over gamma plus 1 rho L, and AR is 2 over gamma plus 1 rho R. And then BL B is gamma minus 1 over gamma plus 1 times PL. And BR is gamma minus 1 over gamma plus 1. Okay, anyway, that's a little bit annoying, but it's straightforward to code. And then in your function that's trying to find this root, as p changes, you use one of these expressions for the left and the right waves. And then you're trying to match this condition for the pressure here. And when you iterate over, you'll eventually converge to P star, which solves the problem. So that connects the right state through a nonlinear wave to the star state. Then we know the relation across the contact, and then connects the left star state to the left state with using either a shock or a rarefaction. This is straightforward to code. You can do that. Once you have that, right, and including it can also choose that there's a right rarefaction in the left. You can do any of these four.
So it's like,
Oh, sorry, yeah. Go ahead.
so like the lowercase f functions here, like they're purely like a numerical tool, right? They don't correspond to anything physical to do with the problem.
Well, they do. They're the way, they're how you connect the left state across a nonlinear wave. So so it's from here.
Yeah.
So just a notational, so we want to stick that stuff in there. Is that clear? So it's just that these functions f just tell you as a function of p, given the left state, how it would connect to the left state. So it's a jump here, and then you can also jump here. And that's what these functions do. And then they allow you to jump from p left to p star, and then from p star to p right. Is that clear? And similarly, yeah. And so what we're doing is we're doing those jumps, these f's, f left and f right, and we're just allowing them to vary with p here, and finding this p star.
So the f function that has no subscript,
It's just defined to be left plus right.
but the ones that don't have a subscript, so that what you're defining, the thing that's being defined, they're
Where?
I guess right there, because the f that doesn't have a left or right.
Oh,
subscript,
yes.
Yeah.
Yes, that's what we're doing.
Yeah. So what does that describe?
That describes the full solution.
The full solution. Right?
Left state connecting to star state, connecting to right state.
Okay.
Okay. Yeah.
Just to clarify, what is there? There's a lowercase a sub L.
No, it should
The
be.
second condition.
Uh,
Of
we're-
it says there's 2a or 2al.
Yeah, that's the sound speed in the left state. That's
Okay.
gamma p left over rho left squared.
And then inside the brackets is that gamma minus 1 over 2 gamma
Yes.
exponent.
Yes, that's exponent,
Okay.
and then this thing minus that.
Right. Okay.
Okay, so you guys can do this. You should do this. And I'll give you the reference. This is from, it's been mentioned, it's from Toro et al. Okay, one last step. Okay, where was I? Oh yeah, it's still here. It's okay, once you have P star, you can use these jump conditions to get P star. Here it is. So now you have everything. Half velocity on the left, that's the velocity on the right, that's the average velocities, then plus half FR of P star. So once you have P star, you can do this. FR P star minus FL of P star. So now you found P star through iteration. Now you have both. So that is the solution to the Riemann problem. So that's the exact solution. Now, somewhat more tedious is getting the solution afterwards. So let's say you know what the solution is. It's some rarefaction wave and some constant states and shock or some contact discontinuity. Then you can use the thermodynamics to actually find the state along any ray. And so if you're along this ray, you're in the rarefaction fan, you have to use the fact that the rarefaction fan doesn't create entropy. So entropy is constant, it expands, so it lowers its density, but in such a way that it holds its entropy constant. So you can use the relation that P has some constant, which depends on the entropy, times rho to the gamma, to get the pressure and density everywhere in the rarefaction fan. Okay, so it's straightforward. It's just the thermodynamics. Okay. All right. So I have 5 minutes, I guess. So I had more than I realized. So I'll. But what I do want to do is, I think likely the most important thing. First, maybe I'll get to this, but there's a very beautiful fully Lagrangian code that you can write in 1D. And that is still really interesting for some explosions and accretion problems in 1D. That's fully Lagrangian. That's really nice. But the problem, of course, in multi-D is the mesh kind of tangles, so it doesn't work for very long. But there's an older code called BH1, for example, which does a Lagrangian step and then remaps onto a Noetherian grid. So that can be cool. So Lagrangian hydro is cool. Ask me about it if you're interested. But what I want to sketch before I stop is approximate Riemann solvers, because you can also get the star states from them, and you could move a face at the star velocity, for example. So what this, there are these things called integral relations, and I'm just going to sketch this and then I'll stop. And the idea is that you define a control volume in space-time. So you have x and t axes, and we know here's 0. There's going to be nonlinear wave like this, shock or rarefaction, nonlinear wave like that, shock or rarefaction. And what we need is the fastest signal speeds and the slowest, the max signal speed and the min signal speed. And these waves are going to travel the distance t, which is the time we're interested in, times the speed of the wave SR. And then similarly, we'll have t times SL here. So this is kind of a Riemann solution. These are the fastest waves. So interior to here is the contact and all that interesting stuff, rarefactions and so on. They're all in there. But our control volume, we can bound it with, let's say, some XL and some XR. That's our control volume here, this box. And it contains our Riemann solution. And so what you do is you integrate over the control volume. What that means effectively is you're kind of smushing together, averaging out in the star state. And this is called the HLL Riemann solver. But the point is you don't have the contact discontinuity. And so you're just taking an average of all that stuff there. And so it's a little bit, it's straightforward, but a little bit complicated. So I'm going to skip the details, and I'm going to give you the answer, which you already have, which is that you can get the HLL flux by defining this constant UHLL, which are given by the initial conditions and the fastest and slowest wave speeds. So by averaging over this solution, you can derive this constant, which just depends on the right state and the left state, and the fluxes in the left and right state. And once you have that value, given your Riemann problem, then you can find the flux. So the bottom line is that you have an HLL flux at the zone interfaces, which are given by the flux on the left. If this is the way it's written in lots of cases, if in this way, an FHLL if you're in between the waves. So, okay, so the only thing I want to say here, F right. Okay, so to make this moving mesh, all you have to do is change that 0 to the speed of your face, right? So if you're moving too fast, faster than the fastest wave, then your solution is just FR, the flux in the right state. If you're moving too slowly, so you're out here, then your flux is just the flux in the left state. But if you're in between those fastest and slowest waves, you're in the star region, and you can use the flux and then also the values of the quantities there to move your face at some other speed, like that. It turns out, and you should try this. So all you're going to do is, in normal HL Riemann solver, you do this because you want to find the thing at x is 0 characteristic. But if you just switch that to some other speed, you'll get either, you can get the appropriate one. Okay, so we've tried this with HLL. It's not great for moving mesh, but there's a very straightforward extension of HLL called HLLC, and I'll give you the reference for that if you'd like, where you restore the contact wave in the approximate Riemann solver, and then you have star state. So you have the what looks like the full solution, but it's an approximate full solution, and then you'll have everything. So that, I'm just going to write that down and then I'll stop. So this is called HLLC. This is by Toro. And so there you have all 4 states. You have flux left, then you have flux left star, and then flux right star, and then flux right. And so it's the left flux at 0. Again, replace that 0 with your speed. And FL is just the flux at the left times your speed at the left. U star L minus UL. And FR plus SR UR star minus UR. And so that, this one is if your speed is between S star and S left. And this one is if your speed is between S star and S right. And this is if 0 is larger than S star. Okay, so this one works really nice in moving mesh codes, this approximate Riemann solver, because it maintains the contact discontinuity between those 2 states. This was too quick, but the point is it's a straightforward algorithm that if you're interested in, look in this book Toro. I think it's section 10.4. And again, you can code this. This is not hard. It's just a little bit more coding, but it's not a big deal. So you can easily write a moving mesh code using the HLL Riemann solver, and you can have your mesh move. That's it. Okay, thanks.